Hi guys, I'm Tianyu. So today I'm going to talk about how to estimate the rate constant of VOC in atmosphere using SARs method. So the VOC stands for the volatile organic compounds, and there are many different ways in the real life we can produce the VOCs. But in this case, we just focus on one example that the airplanes can produce VOCs. Let's talk about the airplane and the crazy stuff released into the atmosphere. The modern aircraft with their fancy films will turn out when they take off, landing, or just going for a joyride. They emit something called VOCs into the atmosphere. VOC stands for the volatile organic compound, and yes, they made a huge impact into the atmosphere. VOCs are like the troublemakers in the air. They mess with the air quality and even contribute to the greenhouse gases. And yes, that's right. They also have a very important role in forming ozone and those particular matters. Now, the big problem is that how can we get rid of these VOCs? We cannot have them floating around forever, right? So some of the VOCs can react with the OH radical in a series of reactions, and what happens then? They are transformed into the good stuff like water and the carbon dioxide. So the VOC is more like a part of the life for teenagers. They will always cause some troubles, make some problems, but eventually they will grow up and will become mature and responsible people to integrate into society. But here's the catch, my friend. There are so many different kinds of hydrocarbons in the VOCs. So basically, the hydrocarbon is one kind of organic compound which only contains hydrogen atoms and carbon atoms. Again, there are thousands of VOCs in the atmosphere, so figuring out their lifetime is not a piece of cake for scientists. And scientists in their labs trying to measure and predict how long these troublemakers will hang around, but it's a tough nut to crack. So there's another method called SARs, which stands for Structure Activity Relationships. So the SARs method trying to predict a lot of other VOCs based on those VOCs we already know their rate constant and they have the similar structure. So to understand the SARs, we can start with the simplest form of alkane. So this is ethane. Ethane is made up of two CH3 groups. And this is one CH3 group. So it contains like one carbon atoms and three hydrogen atoms. So you can also be seen as two identified pieces of Lego stacked on top of each other. And the CH3 groups also has one K parameters. What does the K parameters for CH3 means? It means like how fast does one CH3 groups can react in the atmosphere. But actually, one isolated VH3 group does not exist in the atmosphere. It must be combined with it must be bonded with other parts of molecules or groups. Because two VH3 groups are connected with each other through a carbon-carbon bond, so they will interact with each other. To be more specific here, like this is CH3 number 1, it will receive an impact from the CH3 number 2, and also the CH3 number 2 will receive an impact from the CH3 number 1. So this is like more easy to understand if you are imagine like you are holding hands with your girlfriend and boyfriend. You are not isolated. You will also like your heart will beat faster and you will feel happy. So in this case, in the SARs, we use F parameters to represent the effect of the environment. So in this case, the F parameters will be F CH3 because the F parameters is come from one CH3 groups. Now we move to the second part. We are trying to write the equations for the total rate constant for ethane. As the picture shows here, the CH3 groups already have one K prime. The K prime also means the K parameters for CH3. Also, the CH3 groups will receive the impact from another CH3 groups, so there will be F factors for CH3. And because of the ethane only have two CH3 groups, so they are receive the same impact from each other. So the K total rate constant for ethane will be 2 times K prime times FCH3. So now we can try to solve another alkane. So this is protein. The protein is a little more complicated than the ethane, but the principle of writing the salts equation is the same. So let's look at the structure of the protein. The protein gets two CH3 groups and one CH2 groups. So the CH3 groups here, it has its own K parameters and also will receive the impact from the CH2 groups here. And the CH3 groups here also will have its own K parameters, and it will also receive impact from the CH2 groups. But how can we deal with the CH2 groups? So actually, the CH2 groups here will receive the impact from both sides of the CH3 groups, and it also has its own K parameters. But to be careful here that the K parameters for CH2 is different of the K parameters for CH3. Now we can try to write the equation. So as the picture show here, we can see two CH3 groups both contains 1 K parameters and receive the impact from the CH2, which is also the FCH2 parameters. And now we need to add for the K set. The K set means the K parameters for CH2 groups, and because again the CH2 groups receive the impact from both sides of the CH3, so it will be K set times FCH3 times MCH3. So the total rate constant for protein will be 2 times K prime times FCH3 plus K set times FCH3 times FCH3. Now you can try to solve the salts equation for butane and pentane. Have a try. If you write the correct equation, then congratulations, you have an initial grasp of salts. So now we get the equations of these 4 VOCs, and fortunately, the real rate constant of these 4 alkanes at 298 K have been determined by some scientists in lab. So knowing these values, we can actually calculate the K prime, K sets, FCH2, FCH3 parameters. And after knowing the true values of these 4 parameters, we can calculate out all straight-chained alkanes in atmosphere of their rate constant. In my study, I derived these parameters based on the experimentally determined reaction rate constant for 15 straight-chained alkane and 24 branched alkanes at 298 K. Compared to the value of the parameters derived in Jenkins' paper published in 2018, I referenced more formal data and we came up with small differences in the data, which proves that the method I applied, also the salts method I used, was correct and update the data of the parameters. Using this data, we can predict a relatively accurate values of VOC of alkane even for the currently unknown rate constants. But this is not enough to predict the hydrocarbon VOC because there are so many different kinds of hydrocarbons. We just calculate for branched alkane and straight-chained alkane. So I also calculate the parameter data for cyclid alkanes, terminal alkane, and internal alkanes. And also I try to find their temperature dependence so that the temperature does not have to be limited to 298 K, and we can get a more accurate VOC range for a we can get a more accurate VOC rate constant for a range of temperatures. So the next time you take a flight, don't just look at how high the plane can fly or how long the flight takes to get there. Just remember, this is also leaving a trail of VOCs behind. Maybe someday we can use SARs together to calculate the rate constant of more additional types of VOCs, so we can do our parts for atmospheric chemistry. So let's make the database huge and laying the important foundation for solving VOC removal. Thank you.